Well, so here's where oh, let me also remind you that I've got to be out of the office today from a little bit after 11 till a little bit after noon. I'll get back as quickly as I can. We have a candidate that I have to look at. Anyway, so we have just sort of started down the road of proving fundamental theorem of Galois theory. We had this lemma last time. We've totally conquered this up through part E. We did the L's. We did this L is contained in L double prime last time. I will leave the H is contained in H double prime as an exercise. And finally, the part let's look at by E, L is contained in L double prime. You know that. So now what I'm going to do is, of course, L is a field, so I'll apply this to it. Like C contained what this says is this reverses the order. L triple prime is contained in L prime. So now we've got this part. And notice that by E, of course, L prime is now a group, but by this part of E, any group, in this case L prime, is contained in its double prime. So in particular, L prime is contained in L double prime. And so the other is similar. That is H prime is H triple prime. Let me make a remark here. Using our notation here, F is Galois. Over K, if and only if K is equal to K double prime. Right, because K prime is a set of all automorphisms that fix K, which is all of F. And so if F prime is equal to, right, and so what this essentially says is K prime is G. And so if G prime is K, this is equivalent to say G prime is K. That is the definition of what it means to be Galois. Additionally, this is true for intermediate fields. And Galois over E. If only that E is equal to E double prime. So that's a more general statement than previous. Now, it is going to turn out that for our proof and for other things, notice when you take E and you get E prime, you get a group. When you double prime, you're back to a field. In general, you expect this to contain the original. That's over there. When they're equal, this is going to be important for both the intermediate fields and the subgroup Galois. We call such things closed, which I believe is the last definition you need for your coming up homework. Suppose that X is a subgroup of the Galois group or an intermediate field. Suppose X is either a subgroup of Galois group, capital K, or an intermediate field say K in X F. You say X is closed if X is equal to its double prime. Again, X is always contained in its double prime, but we say it's closed if you get equality. Let me make a remark. This lemma actually gives us kind of an interesting thing in the following sense. Lemma give us a one-to-one correspondence between closed subgroups of the Galois group and closed subfields of the F. F and closed subgroups of Galois. And here's the way this correspondence works. It's just E goes to E prime. So in a certain sense, we've almost got the statement already for the fundamental theorem. So where are we going to go from here? By the way, check this out. You should check with the previous lemma that under the assumption that E is closed, G is closed. If E is closed, then this thing right here has to be closed, and you get this one-to-one correspondence here as well. So now what we've got is we've got the correspondence between closed subfields and closed subgroups. So our strategy is we're going to show that if F is algebraic and Galois over K, then the intermediate fields are closed. And if F is finite dimensional, which is our part of our original assumption, if F also is finite dimensional, then all the subgroups are closed. So what we're going to get is we want to get to be able to say, we've got this correspondence if we know everything is closed. So what we're going to do is we're going to prove that F is algebraic. If F is algebraic Galois, then the intermediate fields are closed. And then the assumption that we actually had was it was a finite extension. And we're going to prove that if it's finite dimensional, then all the subgroups of the Galois groups are all closed as well. So that's kind of where we're going here. So let's start out on this quest. So kind of a heads up on this, we're going to go through the proof of the fundamental theorem of Galois theory. We're going to do this technical jump. Then we're going to talk about splitting fields and do some other stuff to develop things. But later, not too much later in the course, I'm going to show you actually how to compute Galois groups in a number of ways. theoretically, I'm gonna give you, some theorems to compute Galois groups, show you what their significance is, why they're important, things like number theory. And I will give you actually a way to compute Galois group of any field extension, any finite extension of Q that's Galois. So theoretically, you use the technique I'm going to show you in general. I'm going to show you some short techniques for special cases. General technique, you can take a certain amount of comfort in because you can always do it, but never do it, right? Because the technique I'm going to show you is awful. But it works, and so you can take whatever religious faith from that you can. So lemma. Suppose K and F is an extension of intermediate fields. So we've got these fields here. If let's see, then so if I had two intermediate fields here, if the degree of M over L is, so if this is a finite extension here, then the index of M prime and L prime is finite as well. In fact, it's bounded above by the degree of the index. In particular, here, degree of the extension F over K is finite. Then the order of the Galois group of F over K is less than or equal to the degree of the extension. So what will follow from this is if you have an extension of degree 100, then the Galois group has to be a group of degree 100 or less. In fact, we'll find out later that this is in fact an equality. Okay, so let's prove this. So what I'm going to do is I'm going to proceed by induction on the degree of the extension. On N, which is the degree of M over L. Of course, this is assumed to be finite, so I can do this. And notice, of course, if the degree of M over L is 1, then that means that M and L are the same field. And so it's easy because this index is also 1, and here we go, right? So let's assume that N is bigger than 1. That N is bigger than 1. And we assume conclusion for all I less than N. Okay, so we're doing what is it, complete reduction, I guess. So let's first to tackle this, I want to reduce this to a simpler case. bit of a reduction here in the following way. We select a U. We assume we select some U and M is not an L. We can certainly do this because M is now, since N is bigger than one, this extension is bigger than L. So there is something there. And as the degree of M over L is less than infinity, what can you say about U? Right. You must have to use algebraic over L. So let's let F be irreducible polynomial for U. And we'll say that it has degree, say, K bigger than one. Of course, since U is not in L, the degree of polynomial actually has to strictly be bigger than one. Otherwise, you would be in L. So this means that the degree size K, right, which again is bigger than one. And if this is true, degree of M over LU has to be precisely N over K. Of course, that means that K must divide N because this has to be an integer, but more importantly, the product here has to be N. If K is less than N, then what we have is then N over K is strictly between one and N as well. So we have L prime this is equal to L. So first, that is just from multiplicative fact that indices of groups are multiplicative. And what do we have here? Well, by induction, because these are strictly smaller, by induction, we have that this is less than or equal to right. So we've got this defeated as long as except in this case right here. So in particular, we're done unless K is now. What happens in case K is in? Well, in this case, really what's happening, so let me kind of boil this down for you. This is the case where M is back equal to L. So, in the end case, what you have is when you adjoin this root here, that means that this is entirely in, so that means LU is all of M, right? In this case, we're going to do something a little different, rather than specifically construct a map. So what we're going to do is we're going to build a one-to-one map from the set of left cosets of M prime and L to the set of distinct roots of F and L. So outline this. In this case, we can construct a one-to-one function from set of left cosets of M prime L prime to the set of distinct roots of F. Distinct roots. And of course, the cardinality of that is no more than n. Actually, let me see here. Cardinality no more than n. And let's pay attention actually to that distinct business too. Okay, so how are we going to do this? Well, let's let T M prime or how M prime be the left coset. M prime. And sigma in the Galois group of them. So this just means sigma's an automorphism of F that happens to fix M. Since U is in M, sigma U equals U, right? Because remember this root here, U, LU equals M, so these two are the same field, and use an L with M. So we look at this coset, so if you look at tau sigma u, this is tau u. Um, uh, right, now remember what this is, of course, since tau is an L prime. Tau, is in Galois group. F over L, that is, it fixes anything in L. This means that every coset of tau m has the same effect on u. So every element of the coset tau m, of course, this coset consists of a whole bunch of these. I'm sorry, tau m prime. This consists of all these cosets that are tau times something in m prime. This has the same effect on u. And people takes hey, u to whatever tau u is. So we were going to define the map thusly. We define S T. Let me write this way. Let S be the set of its cosets and tau be the set of roots. I'm going to define it this way. My input is some coset here, tau m prime. My output, I want it to be a root of f. Now, everything in this coset has the same effect on u, and it takes tau u. So this should go to tau u. So a previous argument. Over here, this map is well defined. Because the elements of M prime don't affect where U goes, right? Because it freezes U. So everything in this coset takes U to tau U. That's the argument over here. So this is a well-defined map. Coset root, right? Because if U, well, by definition, U is a root of this original polynomial F, then tau of U, tau being in the Galois group of F over L, that fixes polynomial F, and so it takes this to another root, potentially of a root of F. Now, we want to know that this map is 1 to 1. We'll show this is one. Now, of course, remember, this is a map of sets, so can't do anything with kernels or anything like that, but what I can do is suppose that. Suppose I have this coset and that coset going to the same place. Then this means tau u equals tau not u. And this, of course, means that manipulate this a little bit. These are automorphisms. This means tau inverse tau sub zero inverse tau u equals u. So what this equation tells me is this tau inverse tau fixes u. But m is equal to LU. So if this thing fixes U, and we already know it fixes L, then it fixes all of L joined with U, which is M. Everybody okay with that? So in particular, since tau inverse tau is in M prime. Because remember, this is everything in the Galois that fixes everything in M, right? And therefore, if this is in M, that means the cosets tau zero and prime and tau and prime are equal. And so our correspondence here. Right. And so this gives so I have map, one map from my cosets of M prime and L prime to the same place. Therefore, this thing has to be smaller. That is to say, oops, this is very rapid. That's the big one. Okay, any questions on that? Here's one that might not be a shocker here. This is going to look very much like the previous one. What K and F feels and H. And this one, as you may guess, I'm gonna leave this an exercise. I think you'll see why. H in Galois. If the index So now we're sort of doing the mirror image of the previous lemma. The previous lemma, we said, okay, if the degree of the extension is finite, then blah, blah, blah. Now we're saying if the index of the group H and N is finite, then H field then we have this value here. See if you can do this. The previous one, this is very similar. The difference between this one and the previous is my starting point is the group. And then something about fields, whereas the previous one was starting point was fields, and that's about the groups. Okay. So next, what we're going to do is I'm going to give you a lemma that ties together some of this, and we'll sort of highlight our direction. Well, our situation now is we have, yeah, okay. K, L, M, yeah. And H inside J. Galois. Okay. So I've got L and M are intermediate fields of extension F over K and H inside J are subgroups of the Galois group of F over K. A, if L is closed, and the degree of this extension is finite, then M is closed, and you have an equality in the degree versus index. So you have the L is closed field, and M isn't too big, right? So L is closed, and M is finite dimensional over L. Then M is also closed. So M double prime is also equal to M. And this index is equal to the degree of these. I bet you can guess what might happen here. Now we're going to do basically the same thing for the point of view of groups. So if H is closed, so if a little one is closed, and J is not too big, so the index of H and J is finite. The J is also closed, and the index H prime J prime, or I'm sorry, the degree of H prime over J prime is the index of H and J. And C if yes, if it's finite dimensional and Galois over K then all intermediate fields and all subgroups of the Galois group are closed. So all fields between F and K are closed. And all subgroups of Galois group of F of K, these are all closed. And the order Galois group of F of K is equal to so actually, as we pointed out earlier, we've already sort of gotten from our earlier more primitive lemma that we already have a one-to-one correspondence between the closed subfields and the closed subgroups. So if this holds, if all the intermediate fields are closed and all the intermediate subgroups are closed, then this gives us the exact correspondence. Let me make a mark here. Condition B, so this actually is always useful to look at your parents here. Remark B implies that all finite subgroups the Galois F of K are right because all you have to do is take H to be one, J to be a finite group, and then of course this index here is now finite, right? And so that means that if you have right, so if you take H to be one and J to be finite, what this says that one is closed, and if J is finite, and this index is finite, which that means that J is closed, right? So that's kind of cool. Notice that if you believe this part of C, what you do is you specialize the case where F is finite dimensional over K, then every intermediate subgroup is, that's the conclusion we have to go to. This is just kind of a nice observation in general, because when you talk about the Galois group of F over K, you don't necessarily have to be talking about a finite dimensional extension. You talk about something bigger, because this is just the allomorphism of F over K. Okay. So this one basically is an exercise because this follows from very quickly from what we've done before in lemma 8 to 13, 12 and primitive one. So think about this kind of wraps up what we need for correspondence here. Because in our assumption with the original fundamental theorem of Galois theory, let me check this to make sure that I'm not lying to you, but I think that we assume fundamental theorem right, we assume finite Galois. So this basically wraps up correspondence. Now, one of the other things that we have to tackle here, well, it wraps up correspondence in the case we're talking about, where F is finite dimensional and Galois over K. We need a couple of other things because there was that other business about the normality, right? So part of the fundamental theorem said that, okay, if F is Galois over K, then F is Galois over every intermediate extension, but the intermediate extension was not necessarily Galois over K. And in fact, it was if and only if it's, if and only if the M prime was normal in Galois group. So we need to deal with, I need some definitions to deal with this. So let's consider following. Definition. Yes. Let K and E and F be fields. We say that E is stable. What do I mean for the yeah. What does it mean to be a stable extension? It means that sigma E is contained in it for all sigma in Galois group. So if you apply any automorphism of F and you look at what happens to E, it stays in E. E is like Las Vegas, right? Everything that happens in Vegas stays in Vegas, kind of thing. Be careful. I do not mean that sigma fixes it, right? I just mean that everything in E ends up in E. It might permute E quite a bit. Part B of this definition is the let tau be in the Galois group of E over K. So it's an automorphism, maybe not all of F, but of E, and it also fixes K. We say this is extendable to F. If there exists a sigma in Galois group that over K, such that sigma restricted to E precisely now. Let me make an observation. If you have, if tau is extendable, right, then relative to the sigma, that would mean that E is stable relative to this particular sigma. right? Because the fact that this is extendable means that when you apply this down to the subfield E, this is tau, it's not going to be. So any such sigma that extends tau, E must be stable for that particular automorphism. Okay, it's a good place to stop. Any questions? All right. Well, I will see you folks then on Wednesday.